The gradient handled a function with many inputs and one output. But neural networks map many inputs to many outputs, layer to layer. The derivative of such a function is not a vector but a whole matrix, the Jacobian. It is the true engine of backpropagation. Imagine a function that takes several numbers in and gives several numbers out. Now every output can change with respect to every input. So instead of a single slope, we have a full grid of partial derivatives, how output I responds to input j. That grid of every input-output sensitivity is the Jacobian matrix. Each row of the Jacobian is the gradient of one output. Each column shows how one input ripples through to every output. Together, it captures in one object the complete first-order behavior of the transformation. Near any point, the Jacobian is the best linear approximation of the whole function, a matrix that locally stands in for it. And here the chain rule returns in its grandest form. To differentiate a composition of vector functions, you multiply their Jacobians together. The scalar chain rule, multiplying single rates, becomes matrix multiplication of Jacobians. A deep network's overall derivative is just a product of layer Jacobians, chained from output back to input. This is what backpropagation truly computes. Every layer has a Jacobian, and the error is propagated backward by multiplying by them, one after another. Modern automatic differentiation, the magic inside every deep learning framework, is Jacobians and the chain rule, executed at enormous scale automatically. It is why you never differentiate a network by hand. So, the Jacobian. The derivative of a function from many inputs to many outputs, a matrix of every partial derivative. Compositions differentiate by multiplying Jacobians, the chain rule in matrix form. It is backpropagation made general. Next, how we stop a model from memorizing regularization.